Atom. 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 My name is Atom. Since the dawn of time, humans have sought to understand the mysterious world around us. Now, we know that invisible, tiny particles called atoms make up the ground on which we walk, the air that we breathe, and even the very water that we drink. Yet, our modern understanding of the atom is the product of thousands of years of theories and experiments, a very recent development. In 400 BC, Greek philosopher Democritus came up with the idea that the world was made up of tiny particles. He called them atomos, which means uncuttable, because he believed that they were indivisible.
Democritus believed that there were 4 types of particles: earth, water, air, and fire, and that these 4 particles made up everything on Earth. The next major development that resulted in our modern understanding of atomic structure occurred over 2,000 years later. In 1772, scientist Lavoisier found that mass is conserved in a chemical reaction. His results led to one of the fundamental laws of chemical behavior, the law of conservation of matter.
The law of conservation of matter states that matter can neither be created nor destroyed. In any reaction, the exact same amount of matter that goes in comes out again. Let's take a look. Here we have an orange. It weighs just about 1 7/8 ounces. Now let's react it with my fist and weigh the products. Wow, take a look. That's a looker. Would you look at that? It still weighs 1 7/8 ounces. It weighs the same. That's because the matter was neither created nor destroyed, just rearranged. The same thing happens on a much smaller scale to the particles in a log when it burns, or in your body when you burn energy.
In the early 1800s, English chemist John Dalton transcribed 4 principles composing his atomic theory. His 4 postulates were that all matter is made of atoms. Atoms cannot be divided nor destroyed. All atoms of a given element are identical. Compounds are formed by combining 2 or more different atoms. A chemical reaction is caused by atoms rearranging.
Thanks to Dalton, by the early 1800s, we had a better understanding of the behavior of matter. And yet, we did still not know much about its structure. By the 1870s, scientists began using cathode ray tubes to study atoms.
English physicist J.J. Thomson measured how much heat the cathode rays emitted and was able to estimate the mass of the rays. The mass of these rays was about 1,000 times lighter than that of hydrogen, the smallest particle known at the time. This led Thomson to conclude that cathode rays were actually tiny, negatively charged particles called electrons. Next, Thomson applied his knowledge that the atom has a neutral charge. He decided that electrons must be randomly distributed throughout a positively charged atom, like plums and plum pudding. In our version of the plum pudding model, the waffle is the positively charged matrix, and the electrons are the randomly arranged chocolate chips floating around in it.
The next major discovery was made by Ernest Rutherford in 1909. In his experiment, he directed alpha particles at a coated sheet of gold foil. To his surprise, a small number of the particles did not go through the foil, and were instead reflected back. Rutherford realized that while most of an atom is empty space, each one contains a small, very dense, positively charged nucleus, which reflected the positive alpha particles. Shortly after Rutherford's gold foil experiment was published, physicist Niels Bohr used Einstein's principle of electromagnetic energy to predict that electrons are arranged in orbits around a central nucleus based on energy levels.
After Rutherford published his gold foil experiment, physicist Niels Bohr used Einstein's theory of electromagnetic energy to determine that atoms were placed in orbits around a central nucleus, based on energy levels.
Bohr's theory was close to reality, but German physicist Werner Heisenberg proposed the final addition to our model of the atom, the quantum theory. Heisenberg thought that electrons were both particles and waves, so their location could never be exactly determined. In chemistry class, when we reference the s, p, d, or f orbitals, those are the probable regions of electrons which Heisenberg predicted. Today, we have a nearly complete model of the atom. We know that there is a tiny, dense positively charged nucleus containing protons and neutrons. It is surrounded by electrons moving randomly in orbital clouds. These orbitals have shapes specific to their energy levels.
So that is the modern theory of the atom. What a journey it's been! After 2,500 years of theories and experiments, we have built a detailed understanding of the particle that makes up everything we see, touch, and even taste. Yet, there are so many mysteries yet to be solved, and we do not fully understand what the atom has in store for us.